Hello, doctor. My name is Mohammad Tanzim Rashid, and my metric number is 204928. And today we'll be presenting our group project assignment for Engineering Mathematics 1. And the topic that we have selected is application of differentiation in engineering fields. These are our group members, and each of us will be presenting the importance and application of differentiation in fields of engineering, along with examples and its importance. We'll be starting first with the introduction to calculus and differentiation, and then each of us will move on to explaining differentiation in fields of engineering in the following process, and then end our presentation with a proper conclusion. So first, let me give a give a basic introduction to differentiation. Differential calculus mostly deals with the rate of change of one quantity with the respect to another. It's mostly the study of changes of rate of changes of variables compared to other variables, and by this process we can find derivatives. For example, velocity is the rate of change of distance with respect to time in a particular time frame, in a particular direction, I mean. If f of x is a function, then f inverse x is the differentiation of y with respect to x, and where y is the dependent variable and x becomes an independent variable, and f inverse of x is the derivative of the function f of x. So differentiation is a part of calculus, and calculus is a mathematical study of continuous change. It mostly have two major branches. One is differentiation or differential calculus itself, and integral calculus. Physicists use calculus all the time. Calculus is in the base of all the laws in physics. Whenever we are going to study about the rate of change in time or space, we'll either need to use differentiation calculus or integration calculus. If we want to learn about exactly how far something is moving right now and observe an event at any particular time frame, then we have to use differential calculus. Now I'll be presenting my part, which is differentiation in aerospace engineering. Differential calculus is very important for rocket science in every step of the process. For example, when a rocket is leaving the face of the Earth, it needs a certain acceleration to move out of its gravity. Such precise calculation is very complex as the rocket is constantly losing mass as the fuel is burning, and at every point the mass is different. Again, we need to use calculus in order to calculate the amount of deceleration required for the rocket to land at its particular destination. The two most important the two most important equations to understand rocket science are differential equation of rotation and ideal rocket equation or Tsiolkovsky rocket equation. Basically, differential equation of rocket motion is used to find out the thrust force. So for the equation, we first need to consider a small time frame, that is dt. The momentum of the rocket will be p is equal to m minus dm into v plus dv, where m is the initial mass of the rocket and the mass of the rocket decreases by dm as a result of the field combination, which eventually leads the rocket's velocity to be increased by dv, where and v is the initial velocity. Again, the moment of the exhaust gas which is being released by the rocket in the Earth's coordinate system is P2 is equal to dm into v minus u, where u is the exhaust velocity with the respect to the rocket. And after that, we'll imply the law of conservation of the total momentum of the system for these two equations and differentiate the result that we'll get with respect to t, that is time, and we will get our equation t is equal to u into dm by dt. Moving on. Then the next formula is Tchaikovsky rocket equation. This equation is very important to find out the change of velocity of the rocket in any given moment. So this formula is usually derived using calculus from conservation of linear momentum law. The formula goes as follows, like change of velocity of the rocket is equal to velocity of the exhaust into natural logarithm of MO by MF, where MO is the mass of the rocket with fuel and MF is the mass of the rocket without fuel. Here's an example of implying the Tchaikovsky rocket equation in order to find the rate of change of velocity of a rocket in a given situation. The situation being the mass of the rocket is given as 6,000 kg with fuel, and for the time frame, the specific impulse of the rocket engine is 345 seconds, and the amount of fuel is 1,200 kg. At first, we will be finding out the mass of the rocket without fuel. To do that, we have to subtract 1,200 from 6,000 to find it. Then we'll have to find the velocity of the exhaust, which is the specific impulse of the rocket engine into the gravitational force of the Earth. The unit of gravitational force of the Earth is meter per second square. So by this we'll get the velocity of the exhaust. Then we'll put the values of all these variables in the equation, and using calculator we can find the value. It becomes a lot easier to find the rate of the change of velocity, and is the only way to find it using this rocket equation. Thank you. That will be all for me, and I'll be passing it to my friend for the next one. Thank you.
Assalamu alaikum. My name is FAHAD Mohammad SUBHI Alani, and my metric number is 204356. And today I'll be covering the differentiation in civil engineering. So in civil engineering, differentiation helps us in a big way. It helps us to design and maintain the public works, for example, like the designing of road, bridges, energy systems, water systems, railway, and even airports. It helps us to design them and keep them maintained. Not only that, but it also helps with the hydraulic analysis programs, which helps in the design of the storm drain and even the open channel system. They all use differentiation to obtain their results. Not only that, but it also helps us to determine the values of particular functions. For example, to determine the maximum and minimum of values. For example, the maximum and minimum value of a strength of a beam or a column, how much load or how much strength will go into this beam before it snaps or before it breaks and bends. Not only that, but the cost helps us to calculate the cost of, for example, different beams, different columns, different sections of the buildings. It lets us know and calculate the amount of materials that are used in buildings and etc. So right here we have an example that says the wall shown is 8 feet high and stands 20 feet from the building. What is the length of the shortest straight beam that will reach to the side of building from the ground outside the wall? So right here we have a building, we have a wall right here which is 8 feet high, and it's 27 feet far from the building, and then we gotta calculate the shortest straight beam that will reach the side of the building. So what we can do here first is we can use this formula: L to the power of 2 equals y to the power of 2 plus x plus 27 all to the power of 2. So what we need to do right here is get the value of y. So what we can do is y divided by 27 plus x equals to 8 divided by x. And then what we can do is times the y with the x and the a with 27 plus x. We'll have this right here. We need to get rid of this x, so we'll divide both sides by x and we'll have our y value here. So we can do now, we have our y value, take it, put it in that formula. We'll have this, the value all to the power of 2 plus the same one right here, x plus 27 to the power of 2. And then we don't want L to the power of 2, we just want L. So what we do is square root both parts. And then square root is the same as to the power of 1 over 2. And then L here, which is dl over dx, using the differentiation right here, equals to 0. We have equals to 1 over 2 using the derivative rule. Take the power, put it to the front, and then minus it by 1, which will equals to minus 1 over 2. And then the derivative of the inside part. So right here, we're going to have a minus. So what we need to do is keep this part on the top, bring this part to the bottom here, as we can see. Here. So we won't have any minus. We won't have any minus next to the power. And after that, we'll have this equation. This result, we'll do some multiplying, some adding up, and we'll get this right here. So now, due to the dl over dx equaling 2, 0, as we can see right here, we substitute that to the equation so that all equals to 0. And then we multiply both sides by the denominator to simplify everything, make everything simple, so we don't have a lot of numbers to work with. And then we can also do that again when the denominator equals to the x to the power of x to the power of 3, and then we multiply both sides with x to the power of 3, so we can simplify, and so we can have our numerator to equal to 0. And after that, we'll have our final result right here. And then what we can do with that is use the trial and error rule to get our x value, which is gonna equal to x equals to 12 feet. And that's our final value. And that should be all for me. Thank you so much, and I'll pass it to my friends now.
Hello, my name is FARHAN, and my matrix number is 204801. And today I'll be giving a presentation about differentiation in dynamics, which are applicable for engineering. So let us begin. So the formulas needed will be these two. So a common application of differentiation in dynamics is the relationship between speed, velocity, and acceleration. In these problems, we usually are given with a position which is an equation in the form of x equals to something, or s bracket t equals to something, which tells us the object's distance from some reference point. This equation also accounts for direction, so the distance could be negative depending on which direction the object is moving from the reference point. So as I said, these two are the main formulas that we'll be needing. So an example is that suppose a particle is moving along the x-axis, so that its position at time t is given by the formula xt equals to 3t to the power 2 plus 8t minus 4t to the power 3. Compute its velocity and acceleration as a function of t. Next, to decide in which direction the particle is moving when t equals to 1, and whether its velocity and speeds are increasing or decreasing. To find the velocity, we will use velocity and acceleration. We will use the formula that I've told before in the previous slide. So over here, Vt equals to x, the differentiation of xt, which is 6t plus 8 minus 12t to the power 2. And then to find the acceleration at, it's a differentiation of vt, which is the above one, and it comes 6 equals to minus 24t. So this is the simple application of differentiation in dynamics. And then to continue with the question, by giving t equals to 1, we find the velocity and which direction it moves, and if the speed is increasing or decreasing. So This is my presentation, and I'll let my friend continue. Thank you very much.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Said Hafidh, matric number 204716, and I'm going to talk about the differentiation in fluid mechanics. To start with, differentiation is used in material derivative. When we need to find acceleration in material derivative, we have to use differentiation. As we know, the velocity is ui plus vj plus wk. Ij and k signify the component of the velocity in x, y, and z direction. So as you know, is acceleration in the rate change in velocity, and velocity consider the x component, y component, z component, and the time in which the fluid flow. So acceleration, we are going to use the chain rule to obtain the formula which says the partial derivative of v to t plus partial derivative of v with respect to x times dx dt, and partial derivative of v with respect to y dy dt plus partial derivative of v with respect to z dz dt. Here we use this chain rule to obtain this formula. So acceleration is going to be the partial derivative of v with respect to t and partial derivative of v with respect to x with the u component which signifies dx dt, partial derivative of v with respect to y in the v component which signifies dx dy dt, and partial derivative of v with respect to z which signifies nw which signifies dz dt. Here, partial derivative of v with respect to t signifies local acceleration, and the other part signifies convective acceleration. When the local acceleration is equal to 0 and we obtain only convective acceleration, we say that the fluid has steady flow, that is dv dt is equal to 0, and the new acceleration formula is this one. Also, the rate change in the rate change, also differentiation is used, that is the mdt. We obtain rho av by using differentiation. Mass is equal to density times volume, and volume is equal to area times length. But the density and the area are constant, so are putting out, then we obtain the LDT. The rate change of length with time signifies the velocity. So we obtain rho a times velocity from the mdt by using differentiation. But this dmdt in control volume, which has inlet and outlet, can be obtained also by taking the rate of inlet minus the rate of outlet, hence also differentiation is used. I'm going to show you an example where we use differentiation in fluid mechanics. Determine if the flowing liquid is compressible or incompressible. For incompressible fluid, the formula here is applicable, in which is equal to 0. We have given the velocity which says in the I component is x squared plus y squared plus z squared, in the y in the x component is x squared plus y squared plus z squared, in the y component is xy plus yz plus z squared, and in the z component is negative 3xz minus z squared over 2 plus 4. We are told to find if it is compressible or incompressible. So we put it in this formula. Then we are going to differentiate each component. In x squared plus y squared plus z squared, we are going to obtain 2x. Since we differentiate with respect to x, hence y squared and z squared are treated as constant. Same goes to all these other values. And in the last one, if we get is equal to 0, then the fluid is incompressible, and we obtain not equal to 0, the fluid is compressible. Hence, here it is clearly shown that differentiation is very important in fluid mechanics. I'm going to let my friend continue the presentation. Thank you.
Assalamu alaikum. My name is Zaki Mohammad Zaki, and my matric number is 205039. Today I'll be talking about the various ways we can implement and apply differentiation in the electrical engineering field, and also provide simple examples to show you how easy and useful differentiation is in this topic. First of all, differentiation can be used to calculate the voltage across inductors like this one, for example. by using the following formula. Voltage equals the inductance multiplied by the current rate of change over time, which is also known as the derivative of the current. Secondly, differentiation can also be used to calculate the current flowing through a capacitor such as this by using the following formula. Current equals the capacitance multiplied by the voltage rate of change over time, which is also known as the derivative of the voltage. Now, I'll be showing you a simple example for each of these formulas, starting with example 1. We are given an inductor with the inductance of 0.1 Henry and a current flowing through it of 10 t multiplied by e to the power of negative 5 t amps. We are tasked to find the voltage across this inductor. So through the use of our first formula, we can apply both of these variables and find the solution for this answer, for this question, which is the voltage equaling e to the power of negative 5t multiplied by 1 minus 5t volts. And for our next example, we have a capacitor with a capacitance of 5 microfarad having a voltage of 10 cosine 6000 t volts, and we're tasked to calculate the current flowing through it. Through the use of our second formula, we can find the current by applying both of these variables in the formula as seen here, which will lead us to having a current of negative 0.3 sine 6000 t amps. In conclusion, there are many engineering fields that implement differentiation to solve important problems such as aerospace engineering, civil engineering, fluid mechanics engineering, dynamics engineering, and electrical engineering, just to name a few. This clearly illustrates how essential differentiation is in our modern technologically advanced life. Thank you for taking the time to view our presentation. We hope it was very useful and informative.